Well, I didn't like the results I was getting, so I'm making this part 2 of this video to show, um, let me check to see if my audio is good. Yeah, my audio is good. To show my improvements. So we go down to Inventor's Corner, Eric Dollard's LMD, Bewley's transmission line, return unlimited current to the grid. So I made improvements and I pre-charged this so you don't have to build it up from a surge. And it creates a sine wave with arcing spikes that leak back to the midline because of the switches opening, closing. They leak out the voltage. The voltage buildup is a mere 570 plus volts that are required to act as pressure to go against the 240 volts from the mains, the AC mains, in order to send over 16 amps back to the grid. 16.64 amps RMS. So we have some leakage here, some spikes that show that the voltage buildup is leaking back during the switching. And I have two different switches. I have one for maintenance and one for surging. So there's no longer any drainage. This thing will not wind down when you're in maintenance mode, because the clock timer for maintenance mode is running at 190 cycles per second, and the duty cycle is 2 seconds, or excuse me, 2%. So that's maintenance, is 190 hertz, 2%. While surge, a different clock, we have 100 hertz at 2% duty cycle. So a slightly higher frequency. Now, what I learned to do to reduce the voltage here from gigavolts down to just under 600 volts, a lot more reasonable, is I took an idea from my circuit, my first Bewley circuit. The very first Bewley circuit is single-phase AC output. And so the only problem here with this pre-charged circuit, this capacitor pre-charged to 345 volts, is the cycle. The AC cycle is not 60 cycles. And I couldn't figure out for the life of me when I created this. This was the first one in the Bewley series. I now have 7 of this archetype. I couldn't for the life of me figure out how to get two things to coordinate, namely the hertz. Here I have 12 hertz on the voltage here, and for some reason it's double 24 on the watts, but whatever, be that as it may, the amps and the volts are 12, just under 12. I had to have the pre-charge of 345 volts, and then I had to have the right number of amps. And here I have, well, yeah, not the RMS, the peak, 345, and then the peak amps is 130, just under 130. So I couldn't get the amps to go, I couldn't regulate the amps relative to the voltage, independent of also regulating or modifying the cycle time to get it to be 60 cycles. So, you got 12 cycles per second, I mean, what kind of specialty AC motor? Maybe Tesla, because the AC motor was custom made for the Pierce Arrow experiment of 1931. So maybe it was custom made to operate at a different cycle time, faster or slower, Well, little did I know that this is basically, I knew this was an oscillating circuit, and I knew this was an LC circuit, but I've never dealt with that kind of animal before, recently, but I never really dealt with it that well, that much. Well, lo and behold, using that style thinking, I came up with an LRC circuit. See, that was the solution. And so I put in 2 ballast loads, inductors, and I monkeyed with them and got them to be 12 millihenries each, just by rolling, the cursor up and down over it. And then I chose this solder joint to modify, and I also rolled the cursor up and down, the mouse wheel, and I got it to be 120 milliohms. It was previously 1 milliohm to represent the internal resistance of the mains source, the voltage source, the AC voltage source. So I raised it by a factor of 120, and both of these, the insertion of these three parametric values, 2, 12, and they had to be 2. Now, it doesn't matter which way the coils are. I just arbitrarily made it look that way because it looks pretty to me this way. But there had to be 2 of them on either side, and then this resistor, somewhat like that. I don't know all the factors that you can modify. You'll have to toy with it yourself. But I had to have 2, not 1. And then the resistor of 120, and it's interesting, the numbers kind of turn out, 12 millihenries each of 2 of them, and then 120 milliohms. Interesting. To match the parameter of 75 picofarads, so that all 4 of these, I call them my FB, my 4 FBs, to regulate the frequency of the current feedback. Because we have to get it to match the voltage. And once it matches, it wants to lockstep, fall into step with the voltage wave that is coming from the mains, so that there is no reactive power. Other than these spikes, I guess you could call them reactive because they're not a sine wave. But there's otherwise, for the most part, it's mostly so, to get a power factor as close to unity as possible with as little waste as possible. And they want it. If you throw this off, the amps wave off, and then go back, if you change one of these, it'll veer. And then if you change it back, the amps wave phase will veer back in lockstep with the voltage wave. It's so amazing, But so we're creating an AC wave artificially on this side using voltage that is higher than what's coming from the mains, so as to overwhelm the amperage, the current coming from the mains, with current of our own going in the opposite direction back to the mains. And we do it by taking by taking the voltage wave and fashioning our own current wave, depressed, so to speak, or pushed down into the negative total. The whole wave has to be, both peak and trough, has to be on the negative side of the baseline to indicate that there is absolutely no current coming from the grid. It's all going back to the grid. So some of it, no, actually 21.77 nanoamps. So that's where these spikes end up at, negative, just below the midline at 21.71 nanoamps. So let's stop this just to confirm that and read. See, it's the top of these spikes don't even go back to midline. They're separated below the midline by a 21.71 negative nanoamps peak, the peak of these spikes, while the peak of the sine wave is negative 10.94 amps. So the peak of the sine wave is around 11 amps negative, and the trough, if I can find one, the trough is at negative 22.85 amps. Actually, 22.97. Yeah, right. So we got the two value. Well, anyway. So it creates this nice depressed negative-oriented sine wave. And then if you watch this thing, all the amps are going in reverse direction against the hot wire or the hot lead of the AC mains. You never see the little yellow dots reversing themselves and going back in this direction. They go up. It's going clockwise, not, no, excuse me, it's going counterclockwise, not clockwise, because if any current was coming from the mains, this circle here, this LRC circle or circuit, sub-circuit, would be going in a clockwise direction, but it's not. It's going counterclockwise, indicating that there is enough pressure here to force it to do what we want it to do, is to go against the grid and feed the grid current. Now, this is preset. I monkeyed with it, and by chance alone, I managed to get it to be so that the RMS was within my target. My target was 15 amps that I wanted to send back to the grid. And so this is still, the RMS is still less than what the breaker, you know, on a branch circuit of your house is set for, 20 amps. But I don't know if that's 20 amps RMS or 20 amps peak, because our peak here, or our trough I should say, is over 20 in the negative. It's nearly 23 amps negative. So this may not be an appropriate example, but the surge is up to you. How you build it, the circuit will still be the same circuit. You'll just build up a surge. So let's build up a surge here. Let's build up a nice surge and make it more. And each time the clock clicks, we get a spike that's deeper in the negative. So here we've got one now that's suitable for my car. My car runs at 200 amps when you're accelerating. Actually, there's a short surge at around, I think it's 225 amps, and then it drops down to 206. It actually goes to 206. So here we got negative 206.8 in our trough. The RMS, though, is 105. So I don't know what the readings on my car is. Is that RMS, or is that, you know, a peak or trough reading? But we have, you know, RMS around 106 amps, although the trough is 207.07. Actually, it's settled out at 207.07. It took a little while to settle out. Sometimes you have to wait a little bit, you know, in simulator time. It's actually nothing in real time. For this thing to settle out, and so it's settled out at 207.07 negative amps is the trough of this AC wave. It looks flattened, but it's just perspective. Don't see, this one's not flattened, the watts, and the watts is around 50 kilowatts, and that's about right for my car. My car puts out, or consumes I should say, 57 kilowatts from the battery pack. The battery pack, of course, is DC, but it converts the DC to AC, because the motors, the dual motors in my car, my RAV4 EV from 2002, from Toyota, they are actually two AC motors. So once in a while you see the frequency pop in, and it's around 60 hertz. The amps are not showing it to you at the moment, but the volts is showing it to you. So, in any case, is this going down? Maybe it's not maintaining. Maybe it's dropping. 206.76. It's not giving us an RMS anymore. And I had to let's see, I had to change the time step to 5 microseconds so that we can spread out the wave and look at it and see what's happening. So we get all these spikes. Now on the wattage, for some reason the spikes are on both sides. Well, the wave is on both sides. Oh yeah, it's dropping 206.45. So maybe it's not maintenance. Maybe it is drainage. Oh, I get it. It's attempting to maintain it, but it's see, the cycle time here, this was 190 hertz, so maybe this has to be toyed with. It has to be lowered. Yeah, that's right, it's dropping. So we have to actually lower this to try to fine tune, try to find where does do we have to put the cycle time in order to get it to stop dropping, because we want to maintain a steady state. Let's save this. I like this one. Yeah, so it needs a little more tweaking. The surge, of course, you probably don't have to change it. You know, it's a question of how quickly do you want it to surge, you know? So this clock timer is set for 100 hertz at 2% duty cycle, and the surge is a reasonable speed. Now the voltage is up to 6.8 kilovolts, which is still pretty reasonable. You know, it's not some absurd value. The problem was I was building up all the voltage and I was not draining it out. And so it was kind of leaking out, and that's why it was a messy waveform. Um, and I don't like messy. Oh, it went back up. So now you see it's somewhere in between 190 and 189 cycles per second. Now it's actually rising gradually. So I could create two clocks and alternate between them. That's right. I could put two clocks here. That's what I'm going to do. So I will leave you with that thought. Oh, it's pre-charged now to 200 amps. Oh yeah, I gotta change that. Now 200 is my target for accelerating a RAV4 EV, because normally it would be 60, no 50. It'd be 50 amps to run my car in cruising mode. That's how much amps it draws from the battery pack in order to cruise. Well, how many amps, you know, are delivered to the dual motors, the dual AC motors. But when you're accelerating, when you got your pedal to the metal all the way, then it's around 200 amps. It has to drain the battery pack. And so that's why, you know, going up a hill is such a big drain on the car. A steep hill. So, hope you enjoyed this video as much as I do.